A big influence in my life was Frank Oppenheimer, the founder of the Exploratorium in San Francisco. I took this pair of photos of Frank when I began teaching there. Frank and his helpers built this swinging pendulum exhibit. Dark sand placed in the bob of the pendulum leaks from its bottom, making a trace on the conveyor belt beneath. When the conveyor belt is at rest, oscillation of the pendulum traces a straight line. When the belt moves at constant speed, a sine curve is traced. A figure from my book shows a vertical conveyor belt wherein a bob oscillates vertically and traces a sine curve. The blue arrows show the direction of the conveyor belt, the direction of wave travel. A sine curve nicely represents a transverse wave. Vibrations in a transverse wave are perpendicular to the direction of wave travel. The amplitude of the depicted transverse wave is indicated, and the wavelength as well. Examples of transverse waves are those on a stretched string and light waves. Another type of wave is a longitudinal wave, generated by vibratory motion that is along the direction of wave travel rather than perpendicular to it. Both types of waves are shown here. A slinky is a favorite way to distinguish between longitudinal and transverse waves. Shake it back and forth and you produce a longitudinal wave. Shake it up and down and you produce a transverse wave. A common example of a longitudinal wave is sound. Waves of sound consist of series of compressions and rarefactions of air molecules. Shake a paddle to and fro in the midst of ping-pong balls and you produce regions of compression and rarefaction. A vibrating tuning fork does the same. Here's a snapshot of the series of compressions and rarefactions of air inside a pipe next to a vibrating tuning fork. These compressions and rarefactions travel from the tuning fork at a speed of about 340 meters per second. That's the average speed of sound in room temperature air. A loudspeaker pumps out sound waves with a variety of frequencies. Waves of compressed and rarefied air produced by the vibrating cone of the loudspeaker make up the pleasing sound of music that Lillian appreciates. Vibrations of this loudspeaker set up similar vibrations in the microphone, which are displayed on the scope. The shape of waveforms in the scope reveals information about the sound. Another type of wave is a bow wave. Imagine a bug bobbing up and down on the surface of water as shown by this top view looking down. The waves it produces make up a pattern of concentric circles. If the bug swims to the right, still bobbing, and travels as fast as the waves it produces, then a snapshot of the wave pattern looks like this. The waves pile up in front of the bug. We say the waves superimpose directly in front of the bug. When the bug swims faster than the waves it produces, it ideally produces this wave pattern. The waves overlap at the edges and produce a V shape. This is a bow wave, which appears to be dragging behind the bug. Here we see the patterns generated by the bug at various speeds. Note that overlapping at the edges occurs only when the bug swims faster than the wave speed. A more common bow wave is generated by a speedboat knifing through the water. An aircraft moving faster than sound is said to be supersonic and produces much the same, only in 3 dimensions. This is a shock wave. Here's a photo of the shock wave produced by a faster than sound bullet piercing through a sheet of plexiglass. The shock wave is visible due to deflection of light through the compressed and rarefied parts of the air. Look carefully and see a second shock wave originating at the tail of the bullet. Here we return to our sketch of the shock wave produced by a supersonic aircraft. Note the 2 cones making up the overall shock wave. The leading cone is made up of compressions and the second cone of rarefactions. Here's a graph of pressure changes occurring at ground level beneath a supersonic aircraft. A high-pressure cone with the apex at the bow of the aircraft is quickly followed by a low pressure, making an N shape. What occurs is a ba-boom, Double, a sonic boom. Here we see that a shock wave is encountering listener B, and has already encountered listener C, and is about to encounter listener A. The boom moves across the ground at the speed of the aircraft. The aircraft that generated this shock wave may have exceeded the speed of sound many minutes ago. There is much present effort by designers to minimize the effects of the sonic boom produced by supersonic craft, but there's no escaping it. It's just physics. Interesting times. In the next lesson, we'll discuss sound in general. For now, I want to leave you with a question. First, a shock wave consists of a cone, the angle of which depends on the speed of the aircraft that produces it. Here's my question. As a supersonic aircraft increases its speed, does the resulting conical angle of the shock wave open wider? Or does it narrow? Or neither? Until next time, good energy.